Morning. Announcements first. The exam will be held on February 8 from 10 to 12 a.m. This is the result of, first of all, the survey among you who, or how many of you would like to participate in the exam, and our search for a suitable room. It will be held in the large lecture hall of Philosopher's Walk 12. There will be a written announcement, of course, but I wanted to let you know right now. Then, of course, there was the question, will a cheat sheet be allowed? Yes. Go ahead. The main effect of the cheat sheet is anyway that you write it. This means that you should write it yourself and not copy it from somebody else. All right. So far, so good. Do you have questions concerning the exam? Do you have trouble with the date of and the time of the exam? No. Yes. When is the QFT exam? Sorry? In the afternoon. Sorry, guys. Yes. February 8, Thursday. February 8 is a Thursday, I hope, right? Okay, good. All right.
When's the last regular lecture?
Huh? Okay, yes. I'm planning to proceed as follows with the lecture. So February 5 to 9 is the exam week. No lecture that week, obviously. The week before that, so that would be January 29, is that correct? Monday, January 29 to February something. That would be a week that I will use for summarizing the lecture and for answering questions you may have. So this means that next week, starting January 22nd, right? It's going to be the last regular week of the lecture. Okay? Good. So much for that. What did we do last time? The main subject of last time was to derive the radial Jeans equation and then to see how the Jeans equation can relate the mass distribution underlying the dynamics of a stellar system can be related to observable quantities. And the final result of that was the equation. Let me, bless you. The equation that we had, 569, right? That related the line of sight velocity dispersion, which is directly measurable through the width of spectral lines, to the radial kinematic pressure component n sigma r square. That was the key point, right? We have the radial kinematic pressure, given by equation 562, or related by equation 562 to the underlying mass distribution. And given that, we have 569 to relate the line of sight velocity dispersion to the radial kinematic pressure. That was the essential point of the largest fraction of the lecture last week. And then we proceeded to the virial theorem and showed that the virial theorem essentially holds as you know it, if you look at 585 here, namely that 2 times the kinetic energy, which is here written as the trace of the kinetic energy tensor, is minus, important, the trace of the potential energy. Minus the potential energy, or written here as the trace of Chandrasekhar's potential energy tensor. This is a short version of a long version, right? The long version is in 582. And there you see the acceleration of the inertial tensor related to the kinetic energy and the potential energy of the system. We will return to this minus sign today. Okay, so far so good. Do you have questions up to this point? What I'm planning to do this week is now to, first of all, speak briefly about Jean's theorem, then discuss what is called the isothermal sphere solution, and then speak about the Jean's wavelength and the Jean's wave number in the context of stellar dynamical systems. And this will raise a lot of questions about the stability of self-gravitating systems. All right, and conceptually, the discussion about the stability of self-gravitating systems is one of the key points of this week. All right, so far so good. Now, let me briefly repeat our starting point, namely the collisionless Boltzmann equation or the Liouville equation. And F, as always, I think this means shock discontinuities arise, which is correct under certain circumstances, you know, but not of our business today. Okay, F is the phase-space density, as you know it. And now I would like to relate this collisionless Boltzmann equation, from which we started deriving the Jean's equation, or Jean's equations, to what is called an integral of the motion. So in classical mechanics, a physical state is described by the phase-space coordinate, which I here write conventionally as x, v, so the position and the velocity of point mass, for example. And I'm looking at quantities q, which are functions of these phase-space coordinates, of which I require that their total time derivative be 0. Quantities like that are called integrals of the motion, for obvious reasons. So, probably you know the saying that dear children have many names. In this case, integrals of the motion are loosely defined, and this is one definition of an integral of the motion, but there are also others. So this means that integrals of the motion are quantities that everywhere in phase space are conserved along particle trajectories through phase space. This could coincide with constants of the motion, but does not necessarily have to coincide. Right? An integral of the motion will always also be a constant of the motion, but a constant of the motion, that is a quantity that is constant along certain trajectories, does not necessarily have to be an integral of the motion which is defined everywhere in phase space. Right? So you can find niches in phase space where you have constants of the motion that cannot be elevated to the level of an integral of the motion. On the contrary, if you have an integral of the motion, this will be a constant of the motion for all trajectories. Again, right, these are definitions, and definitions are, or those definitions are sometimes made differently or made different detail depending on the author that you look at. But let us assume that we have an integral of the motion defined like that. Then you see that let me write the velocity gradient like this, that this total time derivative vanishing can be translated or can be spelled out like this, right? X dot V dot define the phase-space trajectory. And then, of course, if that is true, this follows. And this means that every integral of the motion, if you compare this equation to the collisionless Boltzmann or the Liouville equation, this thing here, shows you that every integral of the motion is a stationary solution of the Boltzmann equation, the collisionless Boltzmann equation. So here we have already 1/2 of Jean's theorem, namely every integral of the motion is a stationary solution of the collisionless Boltzmann equation. Okay. Now suppose, conversely, you define any function that you like, which depends on phase-space coordinates only through integrals of the motion. So you have integrals of the motion, I1, I2, I3, I4, however many you may have, and you define a function exclusively of these integrals of the motion. Then you immediately see that any function of integrals of the motion will also solve the stationary Boltzmann equation, right? Suppose you have a function g that depends only on integrals of the motion q1 to qn and does not depend on phase-space coordinates in any other way. Then you immediately see that the total time derivative of this thing is the sum written down here, so the sum over the partial derivatives of g with respect to the qi times the total time derivatives of the qi's with respect to the dt, but the qi's are all integrals of the motion, so this is 0. So this means that any function exclusively of integrals of the motion will solve the stationary Boltzmann equation, stationary collisionless Boltzmann equation. And that's the reverse of Jean's theorem. And we can write this out as every function depending on phase-space coordinates through integrals of the motion is a stationary solution of the collisionless Boltzmann equation. So, and both together are Jean's theorem. And this is quite important because that allows us to immediately construct, let's say, what's the plural of Ansatz? You know, an Ansatz is an Ansatz in English, but what's the plural of Ansätze? Ansätzes? I don't know. Okay, that allows us to make Ansätze for solutions of the collisionless Boltzmann equation, depending on symmetry, right? Because we know from Noether's theorems that Any time-independent system conserves energy. Any spherically symmetric system conserves angular momentum, and so on. And then we have integrals of the motion. And then functions of these integrals of the motion will automatically be solutions of the collisionless Boltzmann equation. That's very nice, and we are going to make use of that. There are so-called isolating integrals of the motions, of the motion, and not isolating integrals of the motion. Isolating integrals of the motion reduce phase space by one, reduce the dimension of phase space by 1. An example is the energy shell in quantum field theory. Right, there you have one constant of the or one integral of the motion, the energy, and that reduces the available configuration space to a configuration that falls on the energy shell. Isolating integrals of the motion are very useful because they reduce the configuration space. Not isolating integrals of the motion are essentially useless. Good. Now, armed with that, let us go directly to a simple model for the solution, the joint solution of the collisionless Boltzmann equation and the Poisson equation. We are going to use that for many things, or for several things. And that is the so-called isothermal sphere. You might wonder what the term thermal should mean here, because we have a system that by definition has no collisions. So how do you establish thermal equilibrium in a system without collisions? Well, think of an ideal gas. Right? There you also make the assumption that at least the particles have no potential energy with respect to each other. All right, we'll see about that. So, according to Kleen's theorem, in a spherically symmetric stationary system, we could, for example, say that we want a phase-space distribution that is exclusively a function of the energy and the angular momentum. If that system, in addition, is isotropic, so if the orbits are isotropic, then not only the angular momentum will be conserved, but also the absolute value of the angular momentum. And if I want to further simplify the system, then I can start with a distribution depending on a phase-space distribution depending on energy only. That's what we are going to do. And we know from Kleen's theorem that any function of energy only will solve the stationary Boltzmann equation. Good. Now let's make a transformation here. If I have a test particle with mass m, then its total energy will be given by that expression here if we have a potential phi. I'm going to allow myself to change phi by a constant phi 0. What I'm aiming at by doing that is to lower the potential, lower or increase the potential of the system such that I can keep particles bound in that system, possibly. Okay. All right. Nonetheless, that's an arbitrary constant. We can do with that what we want. And then I'm going to rewrite the energy in the following way. By introducing a new rescaled potential psi, with psi equals minus phi plus phi 0. Okay? And this I'm calling minus m curly E. This is just a notational simplification, no more, no less, right? I'm just rephrasing energy in this way. All right, now I know that any function f of curly E is going to be a stationary solution of the collisionless Boltzmann equation. Good, so let us guess one. And the function that I'm guessing looks like this. It has a constant like n tilde divided by square root 2 pi sigma square to the third power. And then exponential of curly E divided by some constant sigma square. All right. This is what I'm guessing, and obviously this is inspired by the Boltzmann distribution in thermal equilibrium. Right? So if I spell this out, this n tilde divided by the normalization factor here, exponential of psi minus v squared over 2 divided by 1 over sigma square. And now you recognize this as a Gaussian in the velocity, or a Maxwellian in the velocity, in the absolute value of the velocity. So this means that if I integrate this phase-space distribution over the velocity, the result looks like n tilde divided by the normalization factor. Now, an exponential factor that does not depend on velocity, and now I'm integrating over this Gaussian over the velocity. And I'm integrating exponential of minus v squared divided by 2 sigma square over velocity space, and this just cancels the normalization factor here. So this is n tilde times exponential of psi divided by sigma square, and by definition this is n. Okay, the number density, spatial number density of particles. All right. Now this allows me to solve the final equation that I have here for psi, right, for the potential psi. And you see I can write psi equals sigma square ln n minus ln n tilde. Okay? Aha. Of course, this is a possibly misleading way of writing things down, right? Because n and therefore also n tilde are quantities which have a dimension. And of those I can't necessarily take a logarithm. So what I should either write here is ln n and ln n tilde as ln n divided by some normalizing constant that cancels out the dimensions. Or I should leave ln n divided by n tilde, then it would be obvious. I don't think that's going to lead to confusion, will it? And suppose you divide n tilde by 1 over cubic centimeter, you're done. Okay, so let's assume that this does not give a problem. Now, let me relate this to the Poisson equation. Now, by writing this down, and through Jean's theorem, I know that the distribution f is a stationary solution of our fundamental equation, right? The collisionist-Boltzmann equation. But it also has to be a solution of the Poisson equation, right? So it also has to satisfy this equation here. Now, how do we arrange for that? First of all, if I apply the transformation psi equals minus phi plus phi 0 to that, that just results in minus nabla square psi. And on the right-hand side, I'm going to write 4 pi g, the mass of a particle. For simplicity, assuming that they all have the same mass. If they wouldn't, I would have to replace this by an average mass. And that would be the only further complication. So let's not worry about that. And then I need the number density here, if I factor the mass out. And, well, yeah, let me just write n here. Okay. But here I do have a relation already between the potential psi and the number density n, which is logarithmic. So let me just put this in. So this is what I get by combining these two equations. And I'm using spherical symmetry now, which I have assumed anyway. Then, without the factor sigma square here, the Laplacian applied to psi, as written down here, is just this expression here. See, until there's a constant, sigma square is a constant, or I'm assuming sigma square to be a constant. And then what is left of this Laplacian, except for the minus sign and the factor sigma square, is just this expression here. So this is minus 4 pi gm divided by sigma square times n. Okay, now what is left is a second order ordinary differential equation for the number density n, from which we can then reconstruct the phase-space distribution. Now, why is this called why is this model that can be characterized by this differential equation here, why is that called isothermal? Let me return to hydrodynamics for a moment and leave this equation at rest. In fact, it's hydrostatics. And I want to apply spherical symmetry as well to the hydrostatic equation. Then you see it looks like this. Right, the hydrostatic equation is what you get from Euler's equation under static assumptions. And if you remember Euler's equation, looks like this, and you apply the static condition, right? Which says that this total time derivative here of the velocity is 0. Then you directly come here if you, in addition, assume spherical symmetry. All right, so that's the hydrostatic equation under spherical symmetric assumptions. Now, let us further assume that we have to do with a fluid characterized by the ideal gas equation. Okay, so I'm thinking of a gas cloud, for example, that whose gas is described by the ideal gas equation. Then I can write, instead of the left-hand side here, it's the radial derivative of rho kBt divided by m bar, right? I should write number of particles times kBt divided by the volume. So that would be the number density of the particles, which is the mass density divided by the characteristic particle mass. Then I'm here. And on the right-hand side, in spherically symmetric conditions, I can write, instead of minus dr phi, I can write minus gm of r divided by r square. So the mass enclosed by a radius r. As a side remark, this equation here is very often used in certain astrophysical situations, namely in the way that you can now solve it for the mass of an object enclosed by a radius r, which would be r square over g okay, 1 over rho. Now I'm pulling the constants out, kb over m bar, assuming, of course, that the mean mass per particle is constant with radius, which it doesn't have to be, right? Okay, but now we have dr rho times t plus rho times drt. Okay. Now you can pull the factor of 1 over rho in and the factor of t out. You see this is r squared divided by t, kb divided by m bar. Then I get kbt here. Now dr ln rho plus dr ln t. Okay. And this is minus kbt divided by g m bar times radius dr ln rho d ln r plus dr ln t d ln r. That's an equation that you very often encounter. It's beautiful because this just tells you that you need to have an idea of the slope power law slope of the density with radius, and an idea of the slope, the power law slope of the temperature as a function of radius. And very often you get an idea from that, for example, from stellar kinematics or from X-ray emission or whatever, right? And then you have pure numbers here, and you get an estimate of the total mass. Okay, that's just for pointing this out. Now, if I return with this equation here to an isothermal situation, right? That is a situation in which the temperature is constant in radius, then you can pull the kbt over m bar out directly, and what is left is dr ln rho on the right-hand side. And on the left-hand side, you have g over r squared times the mass as a function of radius. And now I'm going to write the mass as a function of radius as a function of density. And then this is 4 pi integral from 0 to r over rho of r prime squared dr prime. All right, now I'm multiplying with r squared. I'm taking the constants to the other side. then things look like that. And now I'm taking it a radial derivative. Okay? So this means that dr r squared dr ln rho is minus 4 pi g m bar divided by kbt. I'm taking the derivative with respect to the radius, so that just gives me r squared times rho of r, and I'm dividing out the 1 over r squared. Okay? Now you see, if you compare this equation to that one, they are identical. Because you can directly insert n because you take the logarithm. So the derivative of the logarithm of the mass of the particle falls out. And here you can replace the density by m bar times n. So you see, if you compare these two equations, and if you set sigma square equals kbt over m bar, then you see the equations are identical. Therefore, the model that is being described here corresponds exactly to what you get in hydrostatics, assuming that you have an isothermal situation. And this is why it's called, why this equation here is taken to describe an isothermal sphere, even if the concept of a temperature in that situation is dubious. But temperature is just a word here for the velocity dispersion sigma square. All right, now what do we do with that? Let's first assume that n could be a power law. Why not, right? So I'm trying to solve this equation now. And for the solution, I make first an ansatz, which is a power law, and I need to find out what C and alpha are. But of course, first of all, I need to find out whether that is indeed a solution of the equation above. That's not so difficult, because you see ln n is ln C minus alpha ln R. So if I take the radial derivative of that, I have minus alpha times the radial derivative of ln R, that's 1 over R times minus alpha. But this just cancels one of these R's here. And then I take the radial derivative. So that's just minus alpha over R squared. So then, on the left-hand side, I have minus alpha over R squared under this ansatz. And this is supposed to be minus 4 pi g divided m divided by sigma square C over R to the power of alpha, right, according to our ansatz for the number density n. Okay, but now you see, obviously, the two sides agree only if alpha is 2. So under this ansatz, you can conclude that alpha has to be 2. And if alpha is 2, then of course you can directly invert this equation here for C, and you get sigma squared divided by 2 pi gn. Okay, this is one solution, and it's an important solution, even though it's completely unrealistic. But what makes it so nice is the following thing. Suppose you have, well, first of all, yeah, that's called the singular isothermal sphere. And singular because as radius goes to 0, the density grows to infinity. Okay, then singular isothermal sphere. Very, very often used in astrophysics as a model for a galaxy. If you have a density that falls off like r squared, the mass grows like the radius. Right? Because if you think of the mass that's m of r, and you have a density that falls of like 1 over r squared, this just becomes a radius, a radial integral over 1. So this will just be, the mass will just be proportional to r. This means that if you set a star on a circular orbit in a mass distribution like that, its velocity is related to the mass by v squared equals gm over r, but the mass grows like r. So that would be the velocity, the orbital velocity of stars in such a system would be constant with radius. And this is at least very close to what we observe. So this, what is called isothermal slope here, has the enormous advantage that it reproduces what is called the flat rotation curves of galaxies. And again, like so often in astronomy and astrophysics, a rotation curve is a misnomer, because what you observe is not the rotation of the system, but the orbital motion of the stars. Nonetheless, this reproduces flat rotation curves. Well, very good. But you expect the density to go to infinity in the core, and you expect the mass to be infinite. And this is not the whole problem, because this means that density will be non-zero out to arbitrary radii. And this means that this particular system here will lose particles all the time to its environment. Right? Because you will have particles at very large distance that are essentially unbound. So this singular isothermal model here is extremely practical and completely unrealistic. But it reproduces flat rotation curves and is therefore very frequently used in astrophysics. What else can you do? Let me use this part of the board to return to this equation here. Because you know, it's a second order ordinary differential equation, so it must have two linearly independent solutions. Well, this is one. There may be a non-singular other. Let's have a look. Let's suppose we have a non-singular solution of this equation here. And again, it will be a solution, if we find one, it will be a solution for the isothermal sphere, but it will then be a non-singular solution. All right, and let us say that we introduce a radial scale R0 such that the radius becomes a dimensionless coordinate x, and we further introduce a finite number density n0 such that n over n0 is a dimensionless expression for the density y. All right. This is, of course, exactly what we did when we spoke about the Lane-Empton equation in hydrodynamics. Right? We introduced the radial scale, we introduced the density scale. Okay. Now, if I do that, I can write the following: 1 over r0 squared. I'm writing this because here you see the powers of r cancel out here. But I have 1 over length square in these two derivatives. So the overall expression must go like 1 over r0 squared. And then I have 1 over x squared dx, x squared dx ln y. Right, and n0 doesn't play a role because as I'm taking the logarithm, I'm just adding a constant here, which drops out when I take the radial derivative. Okay, on the right-hand side, I have the constants minus 4 pi g m divided by sigma square, and now n0 times y. Okay, now we do the obvious, right? What we also did when we dealt with the Lane-Emden equation. Now I'm going to choose r0 such that this whole expression here becomes a constant. And I'm not choosing 1 for this constant, but I'm choosing 9, okay? So this suggests writing r0 square equals sigma square divided by 4 pi g m n0, and I'm writing a factor of 9 into that. So that the whole equation reads 1 over x squared dx, x squared dx ln y equals minus 9 times y. Sorry for the mess here on the board. The 9 just makes sure that the central density, or that the reference density n0 is going to be the central density. I could choose 1 as well, and it would be perfectly legitimate. But then the physical meaning of n0 would be different. Right? Then it wouldn't be at radius 0, but at radius somewhere. Okay, now, before the break, and that's going to be over soon, now, of course, you need to solve that differential equation numerically. And you see, all you need to do for doing that is you need to define these 3 lines. And that will give you a solution of this differential equation with these boundary conditions here. So the first one is the boundary condition of the density function y at r equals 0. I set this to 1. And the other one is the slope y prime of the density function. In other words, I demand that the solution is non-singular. And it just has a flat core. And now, indeed, we do have a solution. It looks like that. The blue one. There's an orange one. The orange one is a crude approximation. It's 1 plus x squared to the power of minus 3/2. And you see out to radius x of approximately 2, 3, 4 or so. That is a good approximation. And beyond that, it doesn't work out quite so well. And you see that the solution of the non-singular isothermal sphere becomes flatter than this approximation. This is a problem. This is a problem. But, okay. Now we have a non-singular solution. All right. We have a non-singular solution that approximately has this slope of minus 2 in the density for a certain range of radii here. And this means that in this range of radii, it reproduces flat rotation curves. Wonderful. We need that for observation. You see that the approximation for large x goes like x to the minus 3. If you integrate that to infinity, it diverges logarithmically. So that means that even the mass of the approximation to the non-singular isothermal sphere is logarithmically divergent. Of course, this doesn't fix the problem that the mass is infinite. The mass contained by the actual solution diverges even more strongly, right? Because the density is falling off less steeply than the approximation. Nonetheless, this is also a model that is frequently used, and very often you find the approximation here, 1 plus x squared to the power of minus 3 halves, named as the non-singular isothermal sphere, which it isn't. It is an approximation with a certain range of validity. And agreed, right, up to here approximately, also, it is an excellent approximation. But beyond that, it isn't. Okay, so if anybody serves you this under the heading of non-singular isothermal sphere, it depends on what you do with it, whether you accept that or not. Okay? So these are the isothermal solutions. Now, let's have a break and then criticize the model further. right. Shall we continue? So now, we have learned about the Jeans theorem, and we've made use of the Jeans theorem. Right? We've seen that every function of integrals of exclusively of integrals of the motion is going to be a stationary solution of the Boltzmann equation, and we made use of that by saying, okay, then let's take an isothermal model and see how far we get. And okay, we get a model that reproduces flat rotation curves very well, and of course has lots of other problems. Okay. Now let me briefly come to the question of equilibrium states in self-gravitating systems. So here we do deal with self-gravitating systems, right? The stars or particles that we are looking at, they move in the joint gravitational potential created by, not by themselves essentially necessarily, but by each other, by the collective system. All right. Can you apply thermodynamics to that? Can you apply thermodynamics to a self-gravitating system? You might say, okay, an interesting approach would be to define entropy by its analogy to information. You write down the so-called Shannon entropy. We integrate over phase space here, and we write this as gamma, and then essentially you do this, right? This would correspond to the thermodynamical entropy. And if you do that, you find that this definition of entropy will be maximized indeed by the isothermal distribution. And whether non-singular or not doesn't play such a big role because it's dominated by very large radii anyway. So the isothermal solution maximizes this kind of entropy. But you've seen from our previous discussion that the isothermal solution cannot be an equilibrium solution because it extends to infinity and therefore keeps losing particles to infinity. So this means that with this definition here, you get in conflict with the usual thermodynamical assumptions. Let me add another argument. You've seen the virial theorem here. And the crucial thing about this virial theorem is the minus sign. It tells you that the kinetic energy is the negative potential energy. And this means that, for example, if the overall system loses particles to the outside, it loses energy because it loses the kinetic energy of these particles. So the kinetic energy will shrink, and the absolute value of the potential energy will increase in response. And this means that the system on the whole will shrink. And this means that the remaining particles will become faster. Okay, that's the consequence of the minus sign here. So this means that this minus sign in the virial theorem implies that self-gravitating systems heat up as they cool down. Right? They cool down by losing energy, and the rest, what remains of them, is going to heat up. And this means that they have a negative heat capacity. And you may know from the stability conditions from thermodynamics that any system that has a negative heat capacity is thermodynamically unstable, obviously, right? Because as it loses energy, its loss of energy is going to increase. So both lines of argument, right? You've seen the entropy there. One arguing with the maximum, the state maximizing the entropy, and the other one just coming from the virial theorem, lead to the conclusion that there is no such thing as equilibrium for a self-gravitating system. But this also means that thermodynamics as a conceptually equilibrium theory cannot be applied to self-gravitating systems. And this also means that the question whether something like the second law of thermodynamics is applicable to gravitational collapse is essentially unsolved. Right? We do not know what the entropy of the universe is. And all the many talks that you hear and statements that you find written that as structures form in the universe, its entropy is going to decrease, have no foundation, because we do not know what the entropy of a self-gravitating system is. Generally, we do not know what the entropy of a system out of equilibrium is. All right. Now, this consequence that self-gravitating systems have a negative heat capacity is the reason why the sun shines. Right? Because as the gas cloud or molecular cloud from which the sun forms is losing particles to the outside, it's going to shrink and heat up. So the fact that it is thermodynamically unstable leads to the heat up of the cloud in the center, and this is only stopped by the onset of fusion. Right, so let's not complain about this negative heat capacity. Right, it keeps us alive. So this minus sign here in the virial theorem is one of the most astonishing things. Nonetheless, right? We take a telescope, we look into the universe, we see objects that appear stable. Right? We see galaxies. We have been living in this galaxy for about 100,000 years. If you think of Homo sapiens, right? If you think of our predecessors as a few million years, if you think of the sun traveling around the center of the Milky Way, it takes about 220 million years for going around. So we have been here for a while, obviously. And the galaxy obviously has been stable for that while. But it must be that all these gravitationally bound objects that we observe are long-lived transient states and not equilibrium states. All right. You find many statements about how something like an increase of entropy or so could be defined for self-gravitating systems. You find them described here. For example, if you start with a small collection of stars, which are next to each other in phase space, the trajectories of these stars in phase space will gradually spread over a larger volume of phase space. They will do so because the trajectories of the individual stars will not only be determined by the gravitational potential of the smooth gravitational potential of the collection of stars, but also because they scatter on potential fluctuations. And there has been a lot of work on what Donald Lyndon Bell first called violent relaxation. It's a nice oxymoron, right? Violent relaxation. In German, you could call this brutale Entspannung. In any case, there has been a lot written about this process of violent relaxation and the scattering of particles or stars or so on potential fluctuations in a self-gravitating system that ultimately leads to a large or a coverage, more or less smooth coverage of a section of phase space. You know from Liouville's theorem, right? If you do not have any collisions, then the phase space distribution or the phase space volume covered by a system will be constant. Okay, so you can only spread out if you do have fluctuations, if you do have collisions with potential fluctuations or direct collisions between stars. And this is supposed to lead to this process called violent relaxation. All right. This is one thing I wanted to add about statements on entropy, stability, equilibrium in self-gravitating systems. Right? The minus sign in the virial theorem prevents self-gravitating systems from having an equilibrium state. And then all concepts of entropy and so on, helpful as they might be, if we had any, would have to deal with this fact. All right, that's what I wanted to say about that, and also about the term violent relaxation that you very often encounter in astrophysical discussions. Very often my impression is that it's being used as, I know how I get here, I know that I am here, and in between some miracle happens that I don't know. Right? We know that at least approximately stable objects exist. We know how their early formation process may happen, and we don't know what happens in the middle. Violent relaxation. All right. Very often you find statements about the entropy of the universe. I mentioned that. If anybody tells you things like that, first ask for the definition of entropy. Right? How do people define entropy when they come to a conclusion like that? The Shannon entropy that I wrote down, right? Distribution times Ln distribution integrated. This is one possibility, but there may be many others. And then the next question would be, how do you deal with thermodynamic equilibrium arguments in a system that obviously has no equilibrium? Good. This is all rather interesting and problematic. Very often, you also find in the literature statements about virialization. I mentioned that already. Right? People don't know what to say else, and then return to the virial theorem and say, okay, we know from the virial theorem that 2 times the trace of the kinetic energy tensor is minus the trace of the potential energy tensor. Okay, yes. If you ignore the evolution, right? If you ignore 1/2 times the second time derivative of the inertial tensor. But we have just seen that there is no such thing as absence of evolution in a self-gravitating system, unless you have an energy source somewhere in the middle. Okay? So again, virialization is very often used in the same way as violent relaxation and a relaxation process. And people speak of virialization as if ultimately you would reach virial equilibrium. This may be an excellent approximation, but nobody really knows. And if you ask, what is your definition of virialization? Then people say, all right, my definition of virialization is that equation 585 holds. But then, of course, this definition or the application of virialization becomes cyclic, and it has no substance anymore. What I think is underlying all of that is that scattering on potential fluctuations and scattering of objects on each other in the course of time completely decorrelate trajectories. And that this decorrelation is ultimately, this decorrelation by scattering is ultimately responsible for the virial theorem to hold. But this is a speculation. Okay, do you have questions up to that point? Do you feel safe in your galactic environment? Okay, now let's come to a further problem with self-gravitating systems. Again, let me return to the collisionless Boltzmann equation. In this form here, so I have already assumed that I can replace V dot by minus the gradient of a potential. So I have implicitly assumed in writing this down that there exists something like a joint potential. Okay. And now I'm doing the obvious thing. I do a perturbative analysis because I want to have a look at what the Jeans, not the Jeans theorem, what the Jeans wave number tells us about stability of objects. Stability of perturbations, I should say. All right, so I'm assuming that I can split up the phase-space distribution as some background, some unperturbed background F0 plus a fluctuation delta F, and for now I'm going to assume that F0 is constant, is spatially constant, which means that on the scale that I would like to assign to these fluctuations here, the background density doesn't change much. So if I do that, then I can write the perturbed and linearized equation as that. So what have I done? I've inserted F0 plus delta F into the original equation, and I've taken into account that F0 must also be a solution of the collisionless Boltzmann equation. So then you would have two terms of that sort, either velocity times the gradient of the phase-space distribution fluctuation, or velocity fluctuation times the gradient of F0. Both would be linear terms, but by this assumption here, the other term goes away. Then I should also include a term like gradient phi 0 times the velocity derivative of delta F. Why not? This would also be a first order. And now comes something into the game that is called the Jeans swindle. You see, Jeans has many things named after himself, even things that Maxwell found. But I think the swindle is original to Jeans. Yeah. Where are you? Newton 2. All right. So now about the Jeans swindle. I'm assuming that by changing the phase-space distribution from F0 to F0 plus delta F, I will also change the gravitational potential to phi 0 plus delta phi, and this must now be 4 pi g m times the velocity space integral of F0 plus delta F. All right. At the same time, I must have this. But we assume this to be spatially constant. Okay? on the other side, I can write the Laplacian like that, right? Because if I do have a spatially constant distribution here, then among other things, this is spherically symmetric. And then I can decompose the Laplacian into spherical polar coordinates. So this must be a constant, whatever that constant is. And now you see, okay, you multiply r squared over, you integrate, you get r cubed, you divide r squared out, you get r, you integrate, you get r squared. So this means that then phi 0 must be r squared, proportional to r squared, about the arbitrarily chosen reference point that you used for integrating. Okay? Well, this would mean that you do have a potential of the background solution that grows like r squared, while you have a background solution that has constant density. But in constant density, you cannot have a gravitational force. Where should it pull? If you have a potential that goes like r squared, you do have a gravitational force that points into the center, into your arbitrarily chosen center. Obviously, both of that cannot be true unless the constant multiplying the r square here would be 0. So this means that the Poisson equation is compatible with constant density only if that density is 0. Right? There is no gravitational potential of a spatially constant solution other than 0. What does that mean? Well, that means that, first of all, a gravitational theory whose field equation is the Poisson equation is not able to describe infinite mass distribution or infinitely extended density distributions unless the density would be 0. Why is that? Because the solutions of the Poisson equation are determined by boundary conditions. You know, in three-dimensional space, for example, the eigenvalues of the Laplacian are just the Fourier modes, right? So you know perfectly well how to compose any solution of the Poisson equation in three-dimensional space, for example. But in order to fix a specific solution, you need to fix the boundary conditions. But of course, in an infinitely extended density distribution, there is no boundary. And this was the reason for Einstein to modify the Poisson equation by introducing a constant, the cosmological constant, and saying that, okay, if I want to do Newtonian gravity theory in an infinitely extended density distribution, I need to have something like a cosmological constant. And then he asked himself, answering yes ultimately, can I introduce the same constant into general relativity? Okay. So there's a profound problem behind that. And the problem is that Newtonian gravity is just not capable of dealing with situations like that. So this means if you want to do that right, then you have to go to general relativity. And then things become easy and no problem anymore. Nonetheless, at the point where we are, right, aiming at setting up a first-order perturbation theory for a self-gravitating system, a self-gravitating collisionless system, we need to pretend that we could subtract a solution phi 0. But we know from these considerations that phi 0 has to be 0, right? And a constant. So The gradient of phi 0 will vanish anyway, and this is why we have to silently drop the other first order term that could be there, right? Gradient phi 0 times d delta f with respect to dv. And the process of discussing that away, or the process of sweeping that under the rug, is called the gene swindle. Because at the time when genes introduced that, there was no general relativity. And for genes, this was an essential problem. Okay? So please accept this, together with my apologies for repeating the gene swindle. But if you want to do this right, you will have to do Einstein-Vlasov theory and kinetic theory in general relativity. All right, so let's accept this equation here. And then, of course, we do the obvious thing that we now did so often. We have now a linearized perturbation equation, and now we decompose the perturbations into plane waves. Lovely. And so all the differential operators will turn into algebraic factors. And this is all nice and swell. And so we get minus I omega delta f. Again, delta f is now, to the right of this vertical line, a Fourier mode. Plus ik times velocity times delta f, right? The ik delta f is the gradient of delta f here. Then we have minus ik delta phi times, there's a scalar product, right? The scalar product between the wave vector k and df0 derived with respect to the vector v. Okay. This is now our perturbation equation. Now, in addition, we need to solve the Poisson equation for the fluctuation delta phi. This should work, right? Because the fluctuations in delta f should be confined to finite space. All right, so yes, so I need to write this down, right? The Laplacian of the potential fluctuation is taken to be 4 pi g times the density fluctuation. Here I would have to write 1 plus the velocity integral of delta f, because f is f0 plus delta f. So here you see the gene swindle again. Okay, I'm assuming that the background solution satisfies nabla square phi 0 equals 4 pi g rho 0, making myself blind for the fact that then rho 0 has to be 0. Okay, if we can do that, yeah, okay, fine. Let me just combine this to write rho 0 here. And then we can also take this to Fourier space. Okay. Now I'm going to do something that is going to be very, very similar to what we did when we worked out the linear response function in a thermal plasma. Right, I'm going to use this is the first equation to solve for delta f. And you see this is going to be this expression here times delta phi divided by kV minus omega. You recognize this term, do you? We use that in linear plasma response theory. And of course, because the origin was exactly the same. All right. And I can drop a joint factor of I. Now I'm going to insert this delta F into the linearized Poisson equation here. And then the whole equation looks like that. And now you see we can combine all of that to write a dispersion relation. I'm going to sort terms and say this prefactor times delta phi must be 0. And again, as in plasma response theory, I can draw one of two conclusions. Either delta phi is 0, well then we don't have any perturbations and we are done. Boring part. Or we say this expression must hold. And this is the dispersion relation for fluctuations in the gravitation potential and the phase-space density alike. Okay. Now, once you encounter a dispersion relation and you want to do stability theory, what do? You search for negative frequencies squared, because then you know that your ansatz of a plane wave is going to grow exponentially in time. So if you want to draw the boundary line between stability and instability, you set the frequency to 0. And if you do that, stability and instability, omega equals 0, and you find let me write it this way here. This must be 0. My goodness. Omega is 0. All right. And now you see you can go on just with a partial integration here and write I'm pulling this wave vector here out front because we are integrating over velocity and not over wave vectors. F0, right? I'm now pulling the velocity space derivative to the other factor. And this gives this expression here, right? So by the partial integration, I would get a minus sign here. By taking the velocity derivative of 1 over k times v, I'm getting another minus sign, so this is plus. And then all that is left is this expression here. You see now I have the scalar product of k with k, so that's a k square, and I can leave this out. Do you have a few more minutes? So we arrive at this expression here, equals 0. And of course, our goal is to find a wave number such that this relation holds. So let me now only deal with the final velocity space integral. And I'm going to write the k times v squared as k v mu squared, where mu is now the cosine of the angle between the vector k, which is fixed during the integration, and the vector v. So I need to solve that. So that is 1 over k squared integral v squared dv from 0 to infinity, 1 over v squared, or f0 of v, right? And f0 of v can only depend on the absolute value of v. Right? Okay, now we have integral over d phi, and we have this integral over mu. I'm deliberately leaving the v square over v square in there. Then I'm getting a factor of 2 pi from the phi integration. The integral over 1 over mu square is minus 1 over mu. I evaluate this at plus and minus, at mu equals plus minus 1. So that gives me a minus 2. So then I have 4 pi and a minus sign. And then I have an integral v squared dv f0 divided by v squared. Okay? And now I'm going to pull the 4 pi in again. And then I have an integral over d3v f0 divided by v squared. And this is just an n0 times the average of 1 over v squared. Okay? If you had a Gaussian, that would be 1 over sigma square. But if you have something more complicated, it looks like that. Okay, so we now can return to our dispersion relation. Now we have a minus sign. Now we divide by k squared. There should only be one factor of n here. And we get this expression here equals to 0. So we can, by definition, this will now be the Jeans wave number, right? Because we set omega to 0. That's the boundary line between stability and instability. And so we can conclude that the Jeans wave number squared is 4 pi t rho Yeah, I think that's correct. Then you get a Jeans wavelength of 2 pi over that. the square root of that for the gene's wavelength. And now let's do one final step. Let's take the virial theorem and say that the kinetic energy 2 times approximately the potential minus the potential energy. And let's approximate these quantities and say, okay, 2 times the kinetic energy for any test particle with mass m will be something like m divided by m times velocity squared, but now I'm writing the velocity squared as 1 over the average of 1 over v squared. That should be gmm over r. The m cancels out. I'm going to write the m as density times r cubed, just to get an estimate. So that allows me to estimate the size of a gravitationally bound object. From which you see that this is 1 over g rho 0 average 1 over c squared, 1 over v squared times the square root. And you see the two are essentially indistinguishable. Right? There is no order of magnitude or so between them. So this means that, taken together, the size of a self-gravitating system is approximately equal to its Jeans wavelength, inevitably. And therefore, it can't be stable. Right? So this is another way of saying the same thing, right? If you do linear perturbation analysis, and then take the statements of linear perturbation theory, that's this one, right? What is the Jeans wavelength? Together with the virial theorem, it tells you that by the virial theorem, self-gravitating systems cannot be stable, right? But because they are necessarily of a size that comes at least very close to their Jeans wavelength. Okay? These are the main difficulties of stellar dynamics. Good. Sorry for running over time. But I think it was necessary to conclude this argument here. And then on Wednesday, we will go on with other things, pretending as if nothing had happened. Thank you very much.